Greetings and welcome to a new video about electric circuits. We continue with the topic of maximum power transfer, and this is our second example. In this example I will look at a different circuit, some different in the, let's say, the drawing, and it will be also helpful to see what we can do there if we have, in this case, multiple sources. So we will of course look at the calculation step by step and also verify these in SPICE simulations. This is the circuit we have given, and the circuit has a set 3 DC voltage sources, 2 volts for the VA, VB is 4 volts and VC is 6 volts. We don't know the resistors here, they are equal to each other. So we have 3 resistors here, R. And there's also a load resistor, also not given. So let's see what the question is. Calculate resistor R to transfer the maximum power of 5 milliwatts to the load resistor. So that's kind of a different question compared to the example number 1. There we need to calculate the load, given for example the resistors and also the DC or the current sources. But now we don't actually know this and also don't know the load, so we have actually more unknowns. But there is an extra known, so there's a given, which is the maximum power. So that will allow us to calculate the R and also the load. So we will of course focus on the R specifically. Now what we do is we need to, of course, in the maximum power transfer theorem, we need to make the Thévenin equivalent circuit of this complete circuit and then make the Thévenin resistance equal to the load resistance. So that's actually our strategy towards the calculation of the resistor R. So the first step is remove the load, in this case the RL, from the circuit. Then the circuit becomes like that. And we can denote the X and Y here to clarify the situation later in great detail. Now, the step 2 is determine now the voltage of the Thévenin circuit. So Thévenin voltage, VTH. This is this voltage, so the open circuit voltage. Now, if I apply Kirchhoff current law at this node, which is also X, I can say, let me also first define my polarities for the resistors. I can say the following. IA, IB and IC actually are flowing in this branch, in this node here. And I can say IA plus IB plus IC must all add up to 0. That is the Kirchhoff current law. Now we can say what is the voltage drop here across this resistor on top. And over that resistor will give you the IA in a similar form for the second one and also for the third one. Now the voltage across this first resistor is VA minus VX. The other one is VB minus VX, and the third one for this one is the VX minus VC minus VX, I mean. And all of them just divide by the same resistor R, so we can see we have this expression. Now, we can of course multiply the left and the right hand side by R, and then will this equation appear. So we have now all the R's disappeared, and we have now VA minus VX, VB minus VX, and VC minus VX. Now we can collect all the VX's and also all the VA's, VB's, and VC we know. Then we have this equation. So we have 3 times VX is equal to VA plus VB plus VC. Now we can now substitute the values, 2, 4, and 6 volts from the given, and that will be 12. And now I have now Vx of 4 volts. That's actually our voltage at node X. Now we know node X is the node we have defined as our node voltage, and node Y is ground. So we can say VTH, this is the Thévenin voltage, is Vx, and that means Thévenin voltage is also 4 volts. So we have this. Now let's also determine the Thévenin resistance, because that is also required for our maximum power transfer theorem. Now we need to short the voltage sources, disable all of them. That means this is shorted, this is shorted, this is shorted. Now the circuit becomes like that. So we have now R, the load is of course still gone, and VA, VB and VC are all shorted. This circuit can be now also simplified, and looking of course in this form, that's the RTH, which is the Thévenin resistance. Then the circuit becomes actually, in a more simple way, drawing is actually this, just R, 3 R's in parallel. And again, between node X and Y, we see the Thévenin resistance. So in order to calculate now the resistance seen between node X and Y, we need to determine this resistance, equivalent resistance of 3 resistors in parallel. And they're all equal to each other. And then we can use actually a nice and simple formula. Rp is R in parallel with R in parallel with R. So if you have 3 resistors equal to each other, you take the one resistor value divided by 3. If you have 20, you divide by 20. That is actually the formula. If you have, of course, 20 times the same resistor value. So then we have this, and it means actually, in simplified form, R over 3. Do we know the R? No, we don't know yet the R, but we know what the Rp is. And Rp is also the Thévenin resistance. So we also know the expression for the Thévenin resistance, which is R over 3. Now that is already an expression that we can use later on for our maximum power transfer. Okay, now moving on to the next step, which is now formation of the Thévenin equivalent circuit using the V Thévenin and the R Thévenin. So Thévenin voltage is known as a value, and Thévenin resistance is also known, but as an expression. So again, this is the model equivalent circuit of Thévenin. Again, the nodes and X and Y. Okay, moving on. This node is X, by the way, and this node is Y. It is actually shown here. Now we connect the load to this circuit. Now we get this. Okay. Now what we want is first define the current and the voltage here. And for maximum power transfer, we require that the load is equal to the Thévenin resistance. And Thévenin resistance is R over 3. That means load is also equal to R over 3. That is actually the conclusion here. So what you need is, you need a resistor, R here, that is 3 times smaller than the load resistance, must be 3 times smaller than this R, or the R must be 3 times larger than this load. So if you know your load, for example, you know that it's 50, in this configuration, you need to have 150 there, 150 there, and also 150 there. Okay. Now, the power delivered to the load resistor is given by this expression, or by this expression. This is also possible. So you can use VL squared over RL or IL squared times RL. I think this is, in this case, easier to work with. So we can say, using the voltage divider rule here, we can calculate VL. VL is RL over R Thévenin plus RL times the Thévenin voltage. We know this. We also know that Thévenin resistance is equal to the load resistor. So that is because of the maximum power transfer. So if I now substitute first this one, I will get a nice result here, which is then RL over 2 times RL, which is 1 over 2. Times 4, we know from the Thévenin voltage, that will give me 2 volts for my load voltage. We can of course also calculate the load current. That is also possible. Just use your V Thévenin and then divide by the total resistor and you will get the IL. But that will be an expression because we don't know the expressions for the R Thévenin, actually the value. So this is maybe easier to work with. So that's actually also the reason why I have chosen for the PL is equal to VL squared over RL. Okay, now we have this. Then we get the following. This is the expression we can use. Substitute the given 5 milliwatts for the left side, PL, 2 squared for my VL, and RL is R over 3. Okay, now that means R over 3 will be then 4 over 0.005. That's actually shown here, and this is 800, and 3 times that will be 2400 ohms or 2.4 kilo ohms for R. That is actually the answer for this question. We can also say, since we know this, the RL must be then 3 times smaller, that will be then 800 ohms. So we also know now the load for this specific situation. Alright, let's also look at the simulation results. We collect all the data we have calculated so far. This is the simulation circuit I have developed in the SPICE. You see the VA, VB and VC, all of them, the values 2, 4 and 6 volts. We also see the 2.4 kilo ohms for the R's, and also the load is 800. I measure here the current, which is the load current, and I also measure the voltage across this load, which is the load voltage. These are this is the ammeter, this is the voltmeter. Now the results are shown here. So you can see the IL is 2.5 milliamps, which also see is the VL is 2 volts. If I now multiply these two values, you will see that this is then 5 milliwatts. What's also an interesting thing is this plot. Load current here, load power here, and a load voltage. A load current is decreasing, starting actually at 5 milliwatts when you have here the load resistor of 0. Because when you make this short, then you start actually at 5 milliamps. And then you decrease because the resistor value here will increase, and you actually have then less current here because of that increasing resistance. So that's actually logical. Okay, we also see the voltage is across these two nodes, X and Y, which is not shown here, but this X and that's Y. That starts at 0 when the load is 0, and then keeps increasing when you increase your load resistance. There's also an interesting plot here by actually using the plot here for the load current and also for the load voltage, the load power, because load power is the multiplication of the load current and the load voltage. And then you get a curve like that, which shows actually already an optimum. So it is not just completely decreasing or constantly increasing. It is increasing, gets some peak value, and then decreases actually for larger values of load resistance. And this is the maximum value of this blue plot, which is the maximum load power of 5 milliwatts, you can see it here, but then for 800 ohms, exactly what we have calculated. So that's actually also the proof. This calculation will give you 0.005 watts. I will also show you now in SPICE how you can generate these plots and also how you can set up this table, and also from this circuit we can discuss more. So let's now jump to SPICE Simulator and also move on with that discussion. Alright, this is now the circuit in SPICE I have already prepared for you. You can see the voltage source VA 2 volts, VB 4 volts, and VC is 6. And we have 3 times the same resistor of 2.4 kilo ohms we have calculated. And the load was 3 times smaller than this R, was 800. And this is the current meter, ammeter, and this is the voltage meter. Okay, now what we can do is we can now go to analysis and do, for example, DC analysis, and then, because this is a DC circuit, and then just calculate the node voltage. And you get directly this 2.5 amps here and 2 volts here. So if you multiply that, you will get 5 milliwatts for this specific situation. You can also click on this component and see actually directly the associated voltage and the current for this RL. Also that for the others, that's 0 because this is 2 volts and it's also 2 volts, so the voltage drop across this top R is 0. For this case it is of course 2 minus 2 volts over that, and for this case it is 6 minus 2 over 2.4k. Okay, that's just for the circuit, but let's also show you how you can generate these plots. You go to analysis again, DC analysis, and go to DC transfer characteristics. That will give you a plot for a specific sweep. Now the input is what you choose. For example, if you want to sweep the load, or you want to sweep or change the VC, or you want to change VB or maybe another resistor, you can choose it from here. You can see R. You don't know actually now precisely which R you're talking about, so you need to actually number them, R1, R2, and R3. That will be better. But we are of course interested in RL, so that doesn't matter. So you select RL, and you also choose the starting value of the RL, and end this, let's say where you end with the value. So you can say 3 kilo ohms or 2.4 or 2.8 kilo ohms. I have chosen actually also in the slideshow. And this is the number of points to make the, let's say, the plot nicer. Okay, now if I now click on OK, I will get the plot for the current and also the voltage. Now let me separate this, it's not visible. This is a load current. Let me make this also pink, so that will all be also fine. And this was our load voltage, that was blue, so let me make it also blue. This is load voltage, and this is the load current. Now you can see it here. I will type in here, for example, 9, or let me make it 8 is better. Then you get directly 400, 800, and then 1.2K will be easier to see. Of course, we are not interested in just the voltage and the current. We are more interested in the power also. So how can we do that also? So let's also look at that. So before we move on, so let's also do, one moment. So let's also do that. What you do is you go to process, so post process, and then let me show it here, and then select these two values. So you actually select these two values and you go to more, and then do this, that is IL, and also VL, and then between here you need to multiply, so you need to choose a basic function, so that is then times. And you do create, and you just name that function, so they can say, okay, I will call that load power. You can also call it something else, just that's fine. So you can now create this. Now it will be created, and I will get the plot. This is another plot. You can see this plot is shown here, and that is the I think it was red, so let me make that maroon, and this was blue, so make that the right colors. So this, you can now see the load power, and if I now click on this, the cursor, and if I now want to go to jump to the right mouse click, global maximum, you will get 5 milliwatts at very close to 800 ohms. Now that is actually also shown here. You can also see what the current and also associated voltages by going to label, legend, and then do this. And you can see directly what the result is. So you can see here IL is 2.5 milliamps and the VL was 2 volts, specifically for 800 ohms. Alright guys, this was for this example about the maximum power transfer for a rather interesting circuit with 3 volt sources given here in this configuration with 3 the same resistors, and we have actually calculated the unknown resistors for a given maximum power transfer for this load. So that was a kind of a different question than the first example. We will of course continue with other examples and other topics to illustrate the concepts in electric circuits in more detail. If you have any questions about this example and also other example, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.